Hello, my name is Mark Elliott. Welcome to the latest webinar from Imaging and Machine Vision Europe. Very pleased that you can join us today. Today we're talking about GigE and the push for higher speed. As everybody knows, there's an awful lot of development work going on by machine vision providers to move to higher speed gigabit Ethernet. Anyone at Vision at Stuttgart earlier this year would have seen so many companies offering faster 5 GigE products. We saw 10 GigE, 25 GigE, even instances of 100 GigE. It's very inspiring. I'm pleased today to be able to welcome two people from companies doing really great work in this area. We've got Marc Damhaut from Euresys and Torsten Wiesinger from Lucid Vision Labs. I'm going to hand over to Marc first of all, and he's going to explain to us how the Vision IP Core is supporting 25 GigE. So over to you, Marc.
Hello, good morning, everyone. Good morning or good afternoon. So my name is Marc from Euresys. I will start with this presentation with a very short company presentation. At Euresys, we design and we sell machine vision components. Our main product is a set of frame grabber cards. We make frame grabbers compatible with CoaXPress, over fiber, with camera link and analog cameras. We also design and sell a set of machine vision software libraries. They are called eVision. They are meant to analyze images and inspection applications. But today we talk about IP cores, and we develop and sell IP cores compatible with GigE Vision, CoaXPress over fibers, USB 3 Vision, and different sensors. So these IP cores are actually developed by our subsidiary Sensor to Image, so they carry the Sensor to Image brand. Our IP cores are meant to help you design your embedded vision system. An embedded vision system can be a standalone system. It can also be a camera. Most of our customers actually are making cameras with our system. So what we are going to talk about today is more particularly our transport layer IP cores, the IP cores that implement one of the machine vision interfaces. And they are really helping you to reduce your product development phase and the time to market. We are going to focus on one IP core in particular today, and this is the GigE Vision IP Core. This is an IP core for FPGA. It is compatible with Xilinx or AMD Xilinx FPGAs. It is compatible with Intel Altera FPGAs. And we are also developing compatibility with microchip polar fired FPGAs, at least for the 1 gigabit per second version. These IP cores are meant to be integrated into your own system, into your own design. So they are compact and they are customizable. They support speeds from 100 megabit per second, of course, so that includes 1 gigabit per second, 2.5, 5 gigabit per second, 10 gigabit per second, and more than that. This is what we are going to talk about today. Very importantly, our IP cores are delivered with a full-featured reference design. So let's talk a little bit more about what is included in the IP core before we jump to the topic of today's presentation. I think it's worth that I explain a bit more what is an IP core for FPGA, because it's more than just the logic that you upload to the FPGA. So an FPGA is a field programmable gate array. That's an electronic component which is highly programmable. In order to program the FPGA, you upload a file, which is a file that describes the logic that goes into the FPGA. So when you design the system, you program that logic using standard language, which in our case is VHDL, but there are different cases. And after compiling all the files using the different development tools provided by the vendor of the FPGA, you upload the resulting file into the FPGA and it executes the logic that you have programmed. So part of the delivery of our IP core, so you see here the list of all the files that are included of our delivery. On the leftmost box, there is a box called FPGA. This describes the set of the files that we deliver and are used by you to program the logic of the FPGA. These VHDL files, can be customized by our customers and depend on what they want to implement inside the system. There is also a set of C files or object files that are meant to program the CPU, which is inside the FPGA. All these files have been designed to work together and implement, in this case, the GigE Vision interface logic. This could also be co-express or USB 3 Vision. At the same time, we also deliver, in the case of GigE Vision, a set of files that go on the other side, on the side of the host PC. And these are software tools that help receive the video, which is streamed from the GigE Vision device. So now that we understand a little bit more the scope of the delivery, I'd like to come back to a very, very important point, is that we do not just deliver files, logic or C files inside our IP core. We deliver them along with what we call the reference design, which is used by our customers to develop their system. So on the left of the slide here, we see a photo of our MVDK, and this one in particular is our MVDK for GigE Vision development. MVDK is our machine vision development kit. This is the kit that we use to as a reference design to deliver our IP core. We have different versions of the kit for different interfaces, and depending on the FPGA that the customer uses, we can also deliver the IP core on an evaluation board, for example, from the provider of the FPGA, Xilinx or Intel or others. So in all cases, the important point is that you do not just get the software files, you also get the development kit, in this case the MVDK, on which you can develop your application, your system, and we deliver to you a fully working system which is used to start the development. Of course, that MVDK will not be used in the final application, and we can see two examples here. Upper right, we have a large part of our customers who develop cameras. So in this case, the development will become much more compact and will be embedded into a camera. But we also have an important part of our customers who develop embedded vision systems. They can do image transfer, processing, or many different kinds of devices. So we see bottom left here an example of a compact vision system that we have developed as a custom design for one of our customers. Now that we understand, I hope, a little bit more about IP cores for FPGA and how we deliver the IP core at sensor to image, let's talk about the GigE Vision IP core in particular. So GigE Vision is a communication interface for vision applications. I would say machine vision or computer vision applications. GigE Vision is based on Ethernet and on Ethernet technology. Very, very important point is that it supports any transport speed and transport media which have been included into Ethernet. It uses, so GigE Vision uses UDP as the low-level transport protocol, and it defines separate communication channels for control, messaging to the device or to the camera, and for streaming video. GigE Vision is developed and maintained by the GigE Vision Technical Committee, which is covered by the A3 Vision and Imaging, so the former AIA. So I come back to the second point here. GigE Vision supports any transport speed and transport media supported by Ethernet. And this is a very, very important and great feature of GigE Vision. Actually, there are a lot of speed and a lot of media, a lot of connectors and cables defined inside the Ethernet standard. So Ethernet is an IEEE standard, as you can see here. Probably when we think of a GigE Vision camera, we think of the most common interface that we use today in machine vision. That would be an RJ45 connector connected to a Cat5, Cat6 cable with a twisted pair copper cable. But actually, there are a lot of different speeds that are supported by Ethernet. Another type of camera that are common today, we have talked about 2.5, 5, 10 gigabit per second, and a completely different interface used by the 10 gigabit per second some 10 gigabit per second cameras is the SFP plus interface. SFP plus is a standard that defines a transceiver, an optical transceiver to connect fibers to devices. And so using an SFP plus transceivers allows a camera to use fiber optics to transmit signals at 10 gigabit per second over very, very long distances. But again, this is only the beginning. You see in the table on the right that QSFP plus works at 40 gigabit per second, QSFP 28 at 100 gigabit per second, and so on. So within the Ethernet standards, we have access to a long list of low-level physical layers that give us plenty of bandwidth. And this is really great because at sensor to image, we see a very high demand for multi-gigabit Ethernet today. This is due to the sensors that become available. There are high resolution and high frame rate sensors that are available today and that require much more than 10 gigabit per second. Some cameras also have different kinds of sensors. There are multi-source cameras, 3D cameras want to carry more data also. But another important application case that we see is that we have requests for aggregating multiple lower speed streams into a single high-speed stream towards a host. And that's a good example of what we could do if we had access to much higher bandwidth Ethernet. So what are the current limits of our GigE IP Core at sensor to image? Now we have a 24 gigabit per second version that we have recently extended to support 64-bit data path. It requires a 400 megahertz clock, which is okay, at least on higher-end FPGAs. But anyway, you need an FPGA which is not really low-end because you need 28 gigabit per second transceivers anyway for that kind of application. However, one of the limits that we face is the use of UDP. Today, using UDP is the limiting factor in all our applications where the receiver is PC-based. We can see on this graph that UDP has served us very well over the years at 1 to 5 gigabit per second. UDP performance is not a problem at all. At 10 gigabit per second, it starts to be a problem. So we think that now we have to think about using a different protocol, at least a different low-level transfer protocol instead of a UDP. Luckily, Ethernet includes many different other protocols. One of them is TCP. TCP provides improved performance, but for the cost of increased latency. So that is a problem on our side. TCP has been used successfully, for example, to use a Wi-Fi 6 camera. So it could be a good option in that kind of application. However, it will not bring us much further than 10 gigabit per second. A real good option here is to use a different protocol, which is called RDMA. RDMA stands for Remote DMA, and one of the ways to use RDMA protocol over Ethernet is to use RoCEv2. We can see here in this presentation that based on our analysis of the bandwidth supports of each of these protocols, RDMA is the way to go if we want to go beyond 10 gigabit per second. So RoCEv2 means Remote DMA over Converged Ethernet. V2 is the version 2. Remote DMA, I don't really have to explain in detail. Let's just remember that it's RDMA, and it's a way to access the memory of the remote device directly. RoCEv2 is part of the InfiniBand architecture specification. And InfiniBand is really a broad international, well-recognized standard. RoCE in itself defines how to run InfiniBand architecture on Ethernet infrastructure. And this is great because this is exactly what we need. We have Ethernet infrastructure because GigE Vision itself is built over Ethernet. RoCE offers hardware offloaded data transfer. It's high performance, low latency, high efficiency, and reliability. Data consistency are all the advantages of RoCEv2. So we think here that we have found the right protocol moving forward and going beyond 10 gigabit per second with remote DMA and RoCE in particular. Now, how to implement it? So how do we go from there? And what did we do at sensor to image? First thing to check is the support by the network cards, because many of our customers anyway, they will stream data from a device, most of the time a camera, towards a PC. So we have to check if RoCE is well supported by network card. And it starts to be the case. We can tell that RoCE and RoCEv2 are typically present and well supported on 10 and 25G network cards with an optical fiber interface. This is the case of the NVIDIA Mellanox cards and chipset. This is the case of the newest Intel cards and chipset, and this is also the case of Marvell and Broadcom chipsets. So we really think that is the way to go, and that we will have better and improved capabilities in the futures in respect of support of this protocol. We have also evaluated if we can implement RoCE and RoCEv2 inside an FPGA. And here we have good news. So based on our prototype, we can see that we have been able to implement RoCEv2 into standard size FPGA. Standard size means a typical size of FPGA, which is used in a small embedded system or a camera. So this table details the number of lookup tables, registers, and block RAMs that are used by our device prototype implementation. This is the second line in the table, compared to the first line, which is our standard UDP GigE Vision reference design. So we can see that we use a comparable amount of lookup tables, of registers. The RoCEv2 implementation requires significantly more block RAMs, but this is to create a frame buffer inside the FPGA. So with our RoCEv2 implementation, we do not need an external frame buffer. So we do not need external memory, which is a great advantage. So what is the current status of our RoCEv2 implementation at Sensor to Image? We have a working prototype. We have demonstrated that prototype at the Vision shows in Stuttgart and Boston. I think that was a bit more than 1 month ago. So at this, in this demonstration, we use our device IP core with RoCEv2 streaming at 25 gigabit per second. And on the other side, we use a standard PC to display the result. A bit more examples here. We have a prototype of IP core that has been implemented into an AMD Xilinx Kintex UltraScale FPGA. And we were running the IP core inside the FPGA evaluation board that you see at the bottom of the slide. On the other side, we use a standard PC with an NVIDIA Mellanox network card. And in between, we use 2 SFP28 transceivers and fiber optics with LC connectors, all running at 25 gigabit per second. On the software side, the system was based on Linux, and we have our own RoCEv2 viewer application to receive the video stream. So this is the status of what we have done at Sensor to Image now. So as a conclusion, we are happy to propose the use of RoCEv2 as a low-level transport protocol for Ethernet streaming at 25G and more. At Sensor to Image, we really believe this is the way to go. Today, we have a prototype IP core that will be made available for evaluation during the first half of 2023. So if you are interested, you can already contact us and we can work together in this direction. Regarding GigE Vision now, and it's a super important point, so RoCEv2 is not part of GigE Vision yet, but Sensor to Image is very active at the GigE Vision Technical Committee. And along with all our partners at the Technical Committee, we work hard to make RoCEv2 part of GigE Vision. So we really hope that in the future, the RoCEv2 protocol will be included into GigE Vision. So thank you very much for your time.
Marc, thank you very much for that. That was very interesting. We've had a couple of questions that have come in while you've been talking. First off, there's a question come in. Are you developing this technology with any other partner?
So the IP core in itself is developed by Sensor to Image and by our engineers. So it's 100% developed by our company in-house. However, the integration of RoCEv2 into GigE Vision and any kind of standardization of the use of RoCEv2 is developed within the GigE Vision Technical Committee. And we work with several partners that within the committee to integrate RoCEv2 inside GigE Vision. So we can really say that this standardization part is super important to us. Of course, we could continue to do streaming at high speed just for our customers using our IP core, but it does not really make sense. We want to continue pushing GigE and GigE Vision towards higher speed. So we work with the committee, with our partners in this direction.
Okay, thank you. And there's a question come in. Does Sensor to Image offer support to implement this new technology?
Yes. So if you purchase the IP core, then we have a support program. There's training first. That's always a very important part. And then we have a maintenance contract that includes support hours during months and years. So we will always be there to help you while you integrate our IP core into your system. We also have what we call a custom design service at Sensor2Image. So if you are not willing to develop the system that you need, then we can execute this development on our side, and then at the end of the development, then you are the owner of the entire system, the source files, and the design files that we have used.
Okay, that's great. And you mentioned first half of 2023 in terms of sort of availability.
Yes.
Is that when you expect? Are you reasonably confident about that time frame?
Oh, yes, we are, because we already have a prototype. Why is this period so long? Actually, if you use exactly the same FPGA as ours, then we are not far away from a delivery. But if you prefer to use a different FPGA, then we will have to port our design, and it is already ongoing. So I mentioned that the demonstration that we had prepared for the Vision Show in Stuttgart used the Xilinx AMD FPGA, but we are already working on porting the same technology towards an Intel FPGA.
Okay, thank you very much. Okay, thank you, Marc. That was really interesting, and I'm sure there'll be some more questions a bit later on. And then for you both, actually, it's a crystal ball question, if you understand the phrasing. Speed, obviously, how fast can it go? What does the future hold? Is there a need for speeds, 100 plus? Can you imagine that kind of future? Where do we think we're going to end up with this kind of journey?
Yeah, I can easily imagine it. I mean, at Euresys, we sell co-express frame grabbers, and we are easily at 40 gigabit per second already, going towards 100. So by using a frame grabber and co-express in our case, we have a lot of applications that are or are going towards that speed. And we have seen the evolution of co-express that started at 6 gigabit per second, then 12, then 4 times 12 to go towards 40. So definitely there is a market for high-speed inspection. There are sensors that are available or are about to be available, requiring several hundreds of gigabit per second. And we can see that the market for these applications, and I speak more for Euresys and Sensor2Image here, the application markets that we see for these applications are inspection in the electronic and semiconductor industry. Think about displays and OLED displays that require a much higher resolution than older generation full HD displays. Think about manufacturing of batteries and film inspection, where our customers want to find smaller and smaller defects in films that are larger and larger. So there is really a high demand for high resolution acquisition and inspection.
Thank you, Marc. I've got a question for Marc here that's come in. Is Euresys exploring the possibility of a GigE Vision frame grabber?
Yeah, the answer is yes, actually. It's more a matter of engineering resources. We have been so busy with co-express that has been super successful for us. But yes, we really believe that there's a market for GigE Vision frame grabber, GigE Vision acquisition cards that are more that are really suitable for this kind of industry. And moving forward, going beyond 10 gigabit per second will also, I would not say require, because we have seen that there are standard network cards that are capable of transporting 100 and more gigabit per second. But having a dedicated card, a card with specific functions, and I'm thinking about buffering the data temporarily. I'm thinking about IOs. I'm thinking about specific features for machine vision of cameras. Then I think that there is also a need for a GigE Vision frame grabbers at that speed in the future.
Okay, thank you, Marc. Well, look, thank you to both of you for spending your time today talking to us. It's been really interesting. Thank you to the people that have come in to ask questions on the presentation today. So thank you to everybody that's joined us, whether you've asked a question or not. Thank you again to Marc from Euresys and Torsten Wiesinger from Lucid Vision Labs. It's been a fascinating session. Thank you to everyone that's going to be watching this on demand on our webcast page at imveurope.com. We will come back to this topic again. There's been a lot of interest, and it's clear from the participation we've had today that there's a lot of interest out there in what's coming next. So certainly something we'll come back to. So thank you to you both. Have a great week, everybody, and thank you for your time.